Aaron Rosetto from National Instruments presents Exploring RFNoC with the UHD Python API. Please welcome Aaron Rosetto.
Hi, everybody. I'm Aaron Rosetto, Principal Architect at NI, and this is Exploring RFNoC with the UHD Python API. I'm honored to be presenting here at GNU Radio Conference 2020. Last year was my very first GRCon, and I absolutely loved it, and I knew this is something I wanted to be a part of. So here I am. The goal of this presentation is to introduce some of the core concepts of the revamped RF network on a chip, or RFNoC architecture, and illustrate them in an interactive fashion using the UHD Python API, showing off different use cases and how the API exposes them to RFNoC users. Hopefully by the end of this presentation, you'll have a better understanding of the capabilities present in the new RFNoC architecture and how you might be able to leverage them for your application, and that Python is a convenient, powerful way to do so. First, a little bit about myself. I started at NI in 2000 working on device drivers and firmware for various data acquisition groups and devices. Last August, I got a chance to join the SDR team to help work on UHD 4.0, which turned out to be a great fit for me because I've dabbled in SDR for nearly 20 years myself, from the FunCube Pro to various RTL SDR-based USB TV tuner dongles, and most recently with the AirSpy for exploring P25 public safety radio systems using the GNU Radio C++ API and several out-of-tree modules. So shout out to the authors of GRFSK4, GROsmocom, and some of the open source digital signal decoder software that I've been using as well as part of my experimentation. Now, time constraints prevent me from taking a deeper dive into the RFNoC architecture as a whole. So I've included a link to Martin Braun's excellent GRCon 2019 UHD 4.0 presentation at the end of this talk if you'd like to learn more. But one of the biggest, most impactful changes to the architecture involves giving the user control over RFNoC image design trade-offs based on the needs of their application. So here's a 30,000-foot view of the RFNoC architecture. Pre-UHD 4.0, the RFNoC architecture allowed full runtime reconfigurability of the NoC block graph topology. That is, how the NoC blocks are connected to each other in the graph. This offered the utmost in flexibility, but the price that the user paid was the FPGA logic element usage to implement that full crossbar switching, which reduced the amount of space available for processing elements. In UHD 4.0, you'll notice that the purple data paths to the NoC blocks are connected to a static router. This static router encodes a fixed topology between the data paths of the NoC blocks. To change the static routing requires reconfiguring the FPGA image. This, of course, offers no runtime flexibility, but sometimes it's not needed. And where it's not needed, the FPGA footprint space savings can be pretty significant. But users can also choose a combination of the two approaches. Notice as well that the stream endpoints and the transport adapters are connected to a full crossbar, allowing any stream endpoint to be connected to any other stream endpoint or transport adapter and reconfigured at runtime. A stream endpoint is more or less the starting or ending point of a data stream, so connections between different statically linked subgraphs can be made and reconfigured as needed by an application without having to resynthesize the FPGA image. We'll see an example of this a little later on. UHD 4.0 ships a UHD Python module which provides Python bindings to the C++ APIs. There are several submodules within the UHD module. The USRP module implements what we call the multi-USRP API, which is a slightly higher level API than this RFNoC level API, but it works across the gamut of all USRP devices. However, today we're going to be focusing on the RFNoC related APIs as a way to delve deeper into the architecture, and that functionality is primarily exposed through the UHD.RFNoC submodule, including such things as creating graphs, discovering graph topologies, configuring blocks, and data interchange with RFNoC graphs. Now, this API, keep in mind, is only available with USRP devices that support the RFNoC architecture. But why Python? Well, first of all, GNU Radio has always done this. It has always provided a rich set of Python bindings to its API, so it's familiar to a lot of GNU Radio users. It's great because there's no compilation step required. You don't have to wait for the compiler to tell you that you missed a semicolon at the end of the line or you misspelt an identifier. You get a nice interactive experience through Python's read evaluate print loop or any of the other third-party add-on REPL loops that Python provides, including niceties such as tab completion. So if I can't remember the different methods supported by a given UHD RFNoC object, I can simply hit tab and have them listed during my interactive console interaction with the API. And finally, there's a very rich ecosystem built up around Python, including numerical processing libraries such as NumPy, which is used by UHD as part of the data interchange with RFNoC graphs, making it really easy to get data in and out of RFNoC and into other popular Python packages that provide numerical processing, because NumPy has become sort of a de facto standard for that kind of thing. So with that as a very, very quick introduction, let's go ahead and start exploring. So I have here a Linux machine running Ubuntu 18.04 LTS with the latest UHD 4.0 release candidate installed on it, connected to a USRP N310 over a pair of SFP Plus connections, which has a custom RFNoC image that I created and installed earlier on it. So I'll fire up the Python interpreter, import the UHD library, and NumPy, so we'll be able to get data off of an RFNoC graph. And graphs are the central concept to RFNoC. So everything to be done with it starts from this graph object. So I create a graph object here targeting my USRP device, and I can run the enumerate static connections method to show how I've configured that static router on the device to connect the NoC blocks together. Now, while this is technically correct, it's not particularly helpful. It's a collection of graph edge objects. So fortunately, that object has a method on it called toString, which I can call to view each edge in a nice humanly readable format. And this is the same output that you would see from the UHD USRP probe utility, which ships with UHD. Note the standard format of the blocks in the RFNoC graph here, known as the block ID. The first element is the device number, followed by a slash, followed by a block name, a number sign, the instance of that block in the graph, colon, and then a port, because blocks can have multiple input and output ports. Now note here that one of the edges is from the radio to the DDC, or digital down converter, and there's another edge between the DDC and the stream endpoint. So through the property of transitivity, we know that there's a path from the radio to the stream endpoint. We'll use that in a little bit. Also notice down here two lone subgraphs. One is an FFT block with a stream endpoint on either side, and the other is a finite impulse response filter block with an SEP on either side. We'll use those in a little while. But let's start by picking one of the blocks and exploring it. And let's start with a radio block. So when you want to interact with a block from the graph, you call getBlock on the graph, passing it the block ID. Now what that returns is an object that is essentially the base class for all NoC blocks. It's common functionality and methods shared by all NoC blocks regardless of what they do. So if you take a look at the methods available on it, you'll see nothing to do with the radio. So to control the radio-specific aspects of this block, you construct a radio control block, which is also available in the RFNoC submodule of UHD, and you pass it that NoC block that you got in the previous step. And then when you look at the API available on this block, you'll notice there's the configuration for the radio in all of its glory. So let's make a simple application where we acquire data from the radio. We know we have a path from the radio to a stream endpoint through the DDC. What we want to do is get samples from the radio to the stream endpoint and then to the host for future processing. So let's do that now. So what we have to do is to explicitly connect the blocks that we want in our graph. So first connection we're going to make is from the radio to the DDC. Now, connect is also used for streamers because we want to connect the DDC to the streamer, but you don't specify the streamer by ID as we did with the radio and the DDC blocks above. We create a receive streamer object, again, through the graph via this create RX streamer object, passing it a pair of parameters. The first parameter is the number of channels in the stream, and the second parameter is some characteristics about the stream through this stream args object. The first parameter in the streamargs object is a string indicating the data type of the samples that we want when we get them from the streamer. And we want nice floating point complex 32-bit values, floats in C terminology. So we'll pass a CPU type of FC32. But RFNoC blocks don't deal in floating point values. They deal in 16-bit fixed point complex values. So the next parameter is the OTW, or over-the-wire type. This indicates the data type that will be interchanged from the UHD driver on the host and the RFNoC graph. And fortunately, UHD will do the conversion back and forth automatically for you, so there's nothing that we have to do after we call receive to get it in the format that we want. So now that we have a streamer, we can connect it up to the output of the DDC. Now notice we didn't even have to specify which stream endpoint to connect to the DDC. This is one thing UHD figures out for us. And finally, we commit the graph. So all of this is great, but we still need to configure the radio and the DDC for our application. We want to tune the radio to a part of the spectrum of interest and return some amount of bandwidth to capture all of the traffic within that portion of the spectrum. So in the interest of saving time, I've got some configuration code already here. Which I will then paste into my Python interpreter, which sets the radio's receive frequency to 853 megahertz, the gain to 65 decibels, tell the radio to receive from antenna port RX2, and a rate of 125 megahertz. So the next thing we need to do is to configure the DDC block, which, again, to call its API, we need an instance of the DDC block controller and passing it the base class of the DDC block that we obtain from the graph. And then to configure the DDC, we tell it the input rate of interest, which, since its samples coming from the radio at 125 megahertz, is 125 megahertz, and an output rate based on the amount of spectrum that we want. So let's set an output rate here of 5 megahertz. Now you'll notice when I did that, I got a warning because the decimation factor in this case, 125 divided by 25, or divided by 5, which is 25, is odd. And so I should expect some passband roll-off. Now let's say that that's undesirable for my application for whatever reason. Here's where properties come into play, because we're going to use one of the properties exposed by the DDC block to set a precise decimation factor. But before we do that, let's take a quick sidebar to talk about the architecture of block controllers in software. At the very lowest level, block IP for RFNoC blocks expose registers in hardware. These registers control how the block works and are specific to each block, and software interacts with them via register reads and writes, or pokes and peeks. The block controller software for a particular block may choose to implement one or more properties. A property is just some kind of configuration data that has a name associated with it and a specific type, whether it be double precision, string, integer, what have you. They may correspond or they may not correspond to the API directly or even to the registers. That's up to the author of the block. They tend to be a little bit higher level than the registers, but they tend to map pretty closely to the registers. Generally, a property has a callback function associated with it that governs what to do when the value of the property changes, generally which is to change the value of one or more registers. Now, block controller software may also choose to implement API functions, generally set and get functions. These represent the highest levels of abstraction of the block's functionality to the user, and a call to set may interact with one or more properties to change the behavior of the hardware. From an application perspective, the block API tends to be the most client-friendly, intuitive means to interact with the block. It's usually adequately documented. But as we've seen, to use this API, it requires having an instance of the actual block controller object implementing that API. But application software can also interact with properties directly because the methods to interact with the properties are on that base class object that you get when you call getBlock on the graph. And similarly, application software can also interact with the registers because the base class exposes access to the register set for the block. Now, this tends not to be recommended because these are less user-friendly methods to interact with the block that generally are poorly documented and may even have unintended side effects. But it does offer an attractive option when you are bootstrapping a new block and you need to configure it quickly, or you need some kind of exceptional behavior that you can only get through interacting with a property or a register. So let's take a look at the properties offered by the DDC block, which we could do by calling getPropertyIDs. The DDC block has a pair of properties, decim, which is the decimation ratio, and freq, which is the frequency shift. There's two of each in this list because there are two ports on the block. So let's use the setProperties method to set an even decimation ratio that will avoid the passband roll-off that we don't want. So we will say setProperties, and we know the name of the property is decim, and we set instant 0 for channel 1 to 24. And now when we call getOutputRate on the block, you'll see that the output rate reflects the new value of the decimation ratio. So we've got a graph, it's committed. We have a streamer object. We've configured the radio and the down converters. So now what we need to do is allocate some space to store the received samples from the radio, which we'll do by taking the output rate, and let's say we want 5 seconds worth, just for this demo. And then we'll also create a numpy array of zeros, just some empty storage, where the data type is the data type that we told the streamer to return the samples to us in, which is complex floating point values. Great. So to get data from the radio, we need to send it a stream command to indicate how the device should send samples to us. So again, in the interest of time, I'm going to cut and paste some code that we already have here. So to create a stream command, I create an instance of the stream command object and pass it the mode that I want, which in this case is num_done. I want to receive a certain number of samples and then be done, no more samples after that point. The number of samples is in the numSamps attribute here, which we calculated earlier, and we're setting stream now to false because I've got a little bit of an issue here. When I send the stream command, I won't have enough time to type in the receive command into the interpreter. So I am going to set a future time event on this stream command to tell it basically to start sending me samples 10 seconds from now. So through the graph object, I get a reference to the motherboard controller from which I can get the timekeeper and get the current time on the radio and add 10 to it. So I could tell it to go in 10 seconds. And when I do that, I'll have to work quickly to issue the stream command and then to call the receive method on the streamer so I can get the samples without causing any sort of underruns or overflows. So quickly here, we'll issue the stream command. And then call receive on the streamer, and it will indicate the number of samples that I get back. And that is 26 million some samples, which is 5 seconds worth at about 5.2 megasamples per second. Great. So now that I've got the data, at this point I can write it to a file, I can process it further, or whatever else our application requires. For instance, we could even plot the data using the matplotlib library. And so in a few seconds, what I'll see is a graph of the real and the imaginary samples returned from the radio. All right, so while that is certainly interactive and certainly instructive, it's definitely not the most convenient way to interact with a USRP. So one other popular method for interacting in a similar fashion in an even more feature-rich way is through Jupyter Notebooks. This is a web-based interactive REPL environment from which documents can be produced, which is great for prototyping, teaching, or report generation. So remember we had a lone FFT block and a lone FIR block. So let's use Jupyter Notebooks to explore those blocks a little bit. So I will start up my Jupyter Notebook here, and I'll load a notebook that I've been working on. And you'll see a notebook just consists of these cells that in which I have sort of common bits of Python code that implement some part of this application. And so this first cell, for instance, imports all the libraries that I need. This next cell, I'll create a graph, just like I did in the interactive example. And then I want to exercise the FFT block. So I'll configure the FFT. I'll then get the block from the graph, construct an FFT block control, and set its API. And we're not going to use the FIR filter in this example. So we could still find it in the graph and call set coefficients. But this next cell here indicates how everything is connected in the graph. So I create a transmit streamer so I can get data into the graph, and a receive streamer to get data out of the graph. And again, I have FC32 and SC16 as my types. Now, because FIR filtered enabled is false, I'm only going to connect the TX streamer to the input of the FFT, and then the FFT output to the receive streamer. So the next thing I'm going to do is just to create a very simple input waveform, which in this case is an impulse. And I'm going to write that to the transmit streamer. That will send it into the RFNoC graph through the FFT. And now I'm going to call receive on the receive streamer to get the results of that. And I will plot them using matplotlib here. And there's the expected flatline output of the FFT of an impulse. Okay. But what I want to show here is how I can reconfigure this image at runtime because of the way that I've configured the FIR and the FFT blocks to be connected to their own stream endpoints. Recall that all of the stream endpoints are connected to a full crossbar. So I can go back here. I can set FIR filtered enabled to true. I'll reconfigure the FIR block with the coefficients for my very simple low-pass filter. And this time, because FIR filtered is enabled, I will connect the transmit streamer up to the input of the FIR block, and then the FIR block to the FFT, and then from the FFT to the receive streamer. So this is a different topology than I had in my first run, but I haven't reconfigured or resynthesized the FPGA. And now again, I'll create my simple impulse, write it to the transmit streamer. It's a little bit longer due to the vagaries of the way that the FIR filter block works. And then I'll call receive, and I will plot the result of that. And there's the expected impulse response for my FIR filter. So in summary, the RFNoC rearchitecture empowers the user to make trade-offs in their design that best fit the application. Fixed topologies can be encoded very efficiently, which allows larger graphs to fill the FPGA. But as you saw in that last example, runtime configuration is available too, if desired, if it is designed in to the topology. There's also, I should mention, a new in-tree switchboard RFNoC block that an intern actually added this past spring, with a configurable number of inputs and outputs and methods to route between them, which offers yet another option for configuring the graph without having to resynthesize a new FPGA image. And the Python UHD API offers access to all of this power in an intuitive, rich fashion. So here are some links to additional resources that go into more depth than I was able to cover in this very short amount of time. There's a link to the RFNoC specification, which goes into the greatest detail on how the nuts and bolts of the RFNoC architecture is implemented. Here's a link to the UHD GitHub repo where you can download the release candidates or releases of the new architecture. Here's a link to last year's presentation by Martin Braun on what we added to UHD 4.0 and talks about more of the features that I wasn't able to go into. And finally, at GRCon this year, we have a couple of workshops where you'll get an opportunity to sit down and create a custom RFNoC image, install it on a radio, and then interact with it through GNU Radio. And here's a couple of other demos and presentations where you'll get more information on UHD 4.0 and the improvements that we've made, and have an opportunity to interact with some of the experts at Ettus and NI who were involved in its creation. And with that, I thank you for your attention. It's been my pleasure to present at GRCon 2020. Enjoy the rest of the conference and stay safe.